Thank you so much for having me. My presentation is called The Intelligent Aggregate Design to Improve Durability and Performance of Your Concrete Mixtures. I want to say a big thanks to my co-authors on this work. I could not have done this without them. Also, a big acknowledgement to the Oklahoma Department of Transportation and to the great Dick Gaynor and Jim Shilstone Sr. They totally inspired me in this work, and I could not have done it without them. Let me tell you a bit about me, why I do what I do. I believe concrete is the best material in the world. I want to make it easier to construct, more durable, lower cost, more sustainable. And what I do is I help build people and tools to make the concrete industry better. And that's why I'm so excited to be here with you today. Now, here's an overview of my talk. I'm going to give you a bit of an introduction to mixture design, talk about the importance of aggregation, and then ultimately talk about the Tarantula Curve. Now, if you look at a concrete mixture, there's many parts of it, but I'm going to ask this question. What is the most important property of concrete? Is it workability, durability, economy, or strength? And I know this is a hard question. Every single project has a different set of requirements, and so it's hard to know exactly what you need. But I would say the most important of these four is workability, because if you don't have workability, you won't be able to make a durable structure. You won't be able to make a structure that people can afford to buy, and you won't be able to get your strength. You've got to have workable concrete. So how do you design a concrete mixture? Well, we all know the ingredients: rock, sand, cement, and water. We all put them together to make this magical material that we all love. But how do I design it? Well, if I want to get durability, I usually focus on water to cement ratio, SEMs like fly ash, slag, or silica fume, and your air content of your concrete if you're concerned about freeze-thaw durability. For strength, again, we need water to cement ratio, and air content can be an issue. For economy, we need to look at the cement content, using local materials, and minimizing our admixture dosages as much as we possibly can. But how do you design for workability? And this is a tough question, because every single job has a different set of requirements. Some might need to be slip formed, like for a pavement. Some might need to be flowable and might need to be pumped. How do you need to know? And we have to figure out how to help you with that today. Now, if you look at designing for workable concrete, it pretty much comes down to the paste content. That's the water plus the binder, the admixtures you use, and the aggregates. And the one people don't think about enough are the aggregates. Did you know that aggregates make up about 75% of the volume of your concrete? Whoa, 75%. That means if you ever hope to get your concrete right, if you ever hope to get workable and get your concrete under control, you must control your aggregates. You must know what's going on with them. But do aggregates really matter? I mean, really, do they really matter? Well, I'm going to show you some mixtures that have the same mixture proportions. So they have the same amount of coarse, same amount of sand, same amount of cement, fly ash, and water. All of them are the same, but we're going to use different gradations. That means different size distribution of the aggregates. Like this, maybe you've seen a plot like this before, where they show you the percentage passing of the aggregates versus the sieve size. These are the smaller aggregates, these are the larger aggregates. Like, what do these mean? What are they about? We're going to give you some tools to help you understand that today. Now, believe it or not, of these mixtures, if the gradation, that size distribution is wrong, I can get really bad performance. And if my size distribution is right, I can get really good performance. For example, if I don't have enough fine sand in my mixture, oh no, look at that. It's horrible. It just falls apart. If I have too much fine sand, it's very stiff concrete. If it's high amounts of intermediate aggregate, it may look like this, and high amounts of coarse aggregate, it may look like this. But if I get it just right, just here in the middle, that's what we want. And so I'm going to give you tools today to help understand this. Again, if you look at how finishing of the concrete works, if I don't have enough fine sand in my mixtures, it looks like this, a bunch of paste covering rocks. If I have too much fine sand, oh no, it's stiff and it's tough. If it's got too much intermediate, you can see the the rock coming out. Too much coarse aggregate. Again, the rock, it's so rocky at the surface, but then in the middle here, that's just right. That's what we're hoping for. That's what we're aiming for. So why would you do this? Why would you aim to control your aggregates? Well, you can reduce your cost. You can improve your strength. You can improve your durability, your sustainability, and you can get a control over your concrete. And that is extremely powerful. Now, I'm going to talk about some of this research that we did at Oklahoma State, and we're going to use a whole suite of tests to work at how the gradation, the size distribution of the aggregates impact the properties and the performance. And we're going to look for slumps from 0 inches, very, very stiff concrete, all the way up to 8 inches, very, very flowable concrete. And we're going to use a whole lot of tests to look at this, but they're practical tests. They're tests that measure, can you place it? Can you drag it? Can you pump it? Can you vibrate it? We want to know how it really performs in the field. And everything I'm going to tell you is on this website, tarantulacurve.com. So you can log on there to learn more. There's free tools, lots of reports, so you can check it out. We're going to use a whole series of workability tests. We're going to use some simple ones like the slump test all the way to much more complicated ones like actual performance in a concrete pump. So the first test I'm going to tell you about is called the float test. And it measures how you finish the concrete, how smooth you can make it. So we're going to use some forms that are about 3 foot wide by about 2 foot long and about 3 inches deep. And we're going to form 3 1-inch diameter holes inside of it. And we're going to see how many passes does it take to smooth the surface and to close those holes and also smooth the surface. So let me show you what that means. So we place the concrete and we strike it off. Then we come in here and with a template, we're going to place 3 1-inch diameter holes. Now, why would we do this? Well, this simulates aggregates being pulled out of the concrete as you finish it. And a person is going to have to finish that and close those holes. We're going to see how hard that is to do. So then we come in here with a float that's trimmed. See how it's trimmed? It only rides on the wood. And then it has a fixed angle in the back. And this float goes over, back, and forth. And we measure how many passes it takes to make a nice, smooth surface and also to close the holes in our concrete at the surface here. So for example, this might be at the beginning, very, very beginning, 0 passes. Here's 2 passes. Here's 4 passes. That's actually pretty good. 6 passes is kind of a good number. If it's more than 6 passes, that's not good. If it's less than 6, that's awesome. And then we also look at surface texture. So we don't need perfect surface texture. If we get something like this, 10 to 30% overall voids, that's awesome. We're very excited about that, and that is very, very good. And again, we say, how many passes does it take to make it be smooth? We also, another test that we're able to do is how it performs in a concrete pump. We're very, very fortunate to have our own concrete pump. Now, this is like kind of the guts of a concrete boom pump that might be used to make a concrete bridge deck. So what we're going to do is when you pump this concrete, it could be the concrete pressures may be too high, just very, very hard for it to move. Or it could be that the mixture segregates inside the pump, and that actually is very dangerous, and we have to watch out for that. So we want to look at these 2 limit states. So we have a whole pipe network. I think of it as like a concrete roller coaster. The concrete comes in here and it goes down, over, up and down, over and over and over again and again and again. And we actually measure the pressure at these different points, point 1, 2, 3, and 4. And how we do that is we use this pressure sensor. Now this sensor is designed to measure oil pressure. And we actually used it in the concrete at the beginning, but it broke. It broke many times. It was like sad, really sad. We wanted to cry. But we came up with a new idea. We said, what if we make this chamber instead? This chamber is actually filled with oil. And see how it's got this flexible membrane? So when you push that surface, the oil increases in pressure inside. And we're able to use that to measure the pressure in the concrete inside the pipe. And the data that we measure looks something like this. This is sensor 1, that's very close to the pump. This is sensor 4, it's the furthest away from the pump. And as the pump fires, as it moves back and forth, we can actually see the pressure it takes to make the piston start to move, and then we can see the concrete start to flow in the line. I think this is very sexy. I mean, look at this. Ooh, it's so nice and elegant and beautiful. Now, what a bad thing that can happen is that if you're pumping the concrete and it starts to segregate. What? Segregate, what does that mean? That means the rock goes to one side and the paste goes to another side. That's actually very dangerous. See the rock here and the paste over here? This causes this to happen. Oh no, this is scary. Look at the pressures. They're very, very high and they're jagged. And this is why it's so dangerous. Segregation during pumping is very dangerous, and we're going to help you avoid that today. We can also look at things at different paste contents, different amounts of cement inside the mixture and how it affects the pumping pressure. This is where it doesn't have very much cement in the mix. This is where it has a little bit more, and this is where it has more. And again, this is the pressure measured during pumping. And more cement it goes down, more cement it goes down from there. We can also look at the amount of sand that's inside the mixture. This is a very low amount of sand, a higher amount of sand, and a higher amount of sand. And again, the pumping pressure actually goes down as you increase the amount of fine sand inside your concrete mixtures. This is really cool stuff that we can learn. So now this is neat. Now how about paving? This is like slip forming. This is like taking concrete in the front that's very, very stiff, and it goes inside a machine and it comes out the other side and it's just beautiful. It's just gorgeous. It comes out, it's flat and it's smooth, and look, it holds an edge, a very nice edge. There's no forms needed in this. And this is often used in concrete paving and sometimes in concrete barrier walls or in curbs. Now, if you look inside a paver, there's one part that's very important, and that is the vibrator. That is the part that shakes the concrete and removes all of the voids. And so we want to understand how the concrete responds to vibration. So we wanted to develop a test that was simple, that measures how the concrete moves under vibration, but also how it holds an edge. It's like a window of workability. It needs to be workable enough, but not too workable. And the slump test, it just doesn't tell us this. So we developed a test called the box test. And it's very, very simple. It is a box with an open top and an open bottom. It's made of two L's that come together. It's 12 inches by 12 inches by 12 inches, and it's held together by these pipe clamps. They're not expensive. They're very simple to use. You hold these boxes together, and then you fill it full of concrete, 9.5 inches towards the top. You take a vibrator and you vibrate down for 3 seconds and then up for 3 seconds. And then you take the clamps off and you pull the edges off the box immediately. You don't wait at all. You do it immediately and you see what happens. Let's see what I'm talking about. Here's the concrete. There's the vibrator coming in, and it consolidates the concrete. And then you immediately take the edges of the pipes clamps off and you look. You go, oh, it's beautiful. What you're looking for is, did the vibration consolidate the concrete? Did the concrete respond to vibration? That's good. You're also looking, did it hold an edge? So let me show you what I'm talking about. See this surface? We can actually use a visual ranking. This would be bad. This would be the best, but we're okay with this. This is okay. This is also good, but these, not good. We want minimal surface voids. That means that our vibrator has done a good job of consolidating the concrete. We also look at the edge. Is the edge falling or not? Because we don't want our mixture to be too workable. So here's a picture. This is very good, very, very straight. That's great. Here's a mixture where it's falling over. Not good, not good. So this box test looks at the window of workability. It's helpful when you're designing mixtures in the lab, when you're trial batching in the field, when you're troubleshooting field problems, and it's like having a miniature paver. It's very, very beneficial. So what we did is we looked at over 650 concrete mixtures, more than 13 coarse aggregates, 4 fine aggregates. We went from low workability, that's like 0-inch slump, all the way to 8-inch slump, very high workable concrete. We looked at different aggregate gradations, different paste contents, different water cement ratios, different water reducer dosages. And what I'm going to do is I'm going to take this vast, huge research and summarize it on one page. One page. And this is the Tarantula Curve. This is very valuable. We took all of our lessons and put them on this one curve. This is the sieve size down here. Sieve. This is the small aggregates. This is the large aggregates. And this is the amount retained, the amount kept on each one of these sieve sizes. There's another check you do up here where you look at how much coarse sand you have, and there's another check that you have for how much fine sand. And this is called the Tarantula Curve because I think it looks like a tarantula. See, that's a spider, tarantula. This is leg, leg, leg. This is the head. This is the body. Tarantula, right? Again, you can find more information at tarantulacurve.com. I also have videos that tell us about this, that teach you how to use this at tylerlake.com/tarantula videos. Now, we're going to take these type of sieve analysis. You've probably seen these before. Sieve size versus the percent passing. And we're going to turn it into a plot or a graph that looks like this. Percent retained. It's how much is kept on each one of these sieves. How much is kept. So this is the individual gradation. And we're going to make a combined gradation. We're going to combine, take a certain amount of this aggregate, a certain amount of this aggregate, and a certain amount of this aggregate, and look at the combined gradation. And that is what's going to go inside the Tarantula Curve. Let's start talking over here. Let's prove to you why this works. So here's the plan. We're going to use these workability tests, all of the workability tests I told you about before, to show you how the gradation impacts performance. And then we're going to systematically change their gradation, and we're going to see how the performance is. And this, again, helps us establish limits. So this is the percent retained I was telling you about before. And here is the sieve size. And now what's going to happen is this mixture, this gradation here and here is poor, not good. And we're going to decrease this aggregate and increase this aggregate, decrease the coarse and increase the intermediate. And we're going to see what happens. Now, in this curve, everything has to total to 100%. So that means when I go down in one area, I have to go up in another area. So let's look. So as we go down here, this went up and it got moderate. And then it got good, 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 back to moderate. Oh no, it's poor again. And let's look. This is very important, very, very important. Poor, good, poor. There's like this boundary. There's some areas where things are bad, some areas where things are bad, but right in the middle, it's good. We're going to see this same trend over and over and over again. So again, if you look at the slump, where it had a high amount of coarse, you can see the coarse is coming out. Where it has a high amount of intermediate, oh, it's stiff. But right in the middle, that's good. If you look at finishing, again, if you have too much intermediate, it's very, very rough on the surface. Too much coarse, very, very rough. But right in the middle, that's good. Let's also look at these things called valleys. Valleys are this point where we can remove a certain sieve. For example, some people think that if I get too low in a certain sieve, I'm going to have problems. So what we did is we removed this out, took it out, totally removed it. And you can see this goes down, but this is still good. This mix is good. Now we're going to remove out the ½ inch as well. Remove this and this. So going down isn't necessarily bad. It's about not getting too high. That's really important. These are all good, 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 good. They performed really, really well. What's important is not going too high in this gradation. So as long as your percent retained was within the limits, 20% is a good idea, a good value for the 3/4 inch to the number 4-inch sieve. But as soon as you start to go over this limit, that's when things start to get bad. You have to watch out for that. And you can have a double valley or a single valley, and it's okay as long as you don't go above 20%. Now let's talk about sand. Sand is very important for concrete, and it's something that we don't understand. Oftentimes, we use something called the fineness modulus to describe our sand gradation, the fineness modulus. It's like taking an entire curve of the sand and describing it with one number. And it's very, very useful, and we've used it for a long, long period of time. But when you use a manufactured sand or a blended sand, it doesn't work very well. Let me explain what I'm talking about. So here is the percent retained curve. Here is the sieve number, and you can see the shape of the curve. It goes up and it goes down. All of these have a same fineness modulus of 2.54. But now I want to show you, see these? All three of these also have the same fineness modulus, 2.54, but the curves are very, very different. And that's what I'm trying to say. We need to better understand these curves, and we can't just use our same trick of using the fineness modulus over and over again. Now, the fineness modulus is useful, but it's challenging to explain a single gradation with a single number. And so we need to look at these sands in more detail. And our research has shown that there's two different types of sands. There's coarse sand and there's fine sand. Just kind of like coarse aggregate. There's coarse aggregate and intermediate aggregate. We kind of find the same thing true with sands. Coarse sand is between number 4 and number 30, and the fine sand is between number 30 and the number 200. And I'm going to explain these and show you why they're important. Let's first talk about the coarse sand. Again, that's the number 8 through the number 30. So one thing we did that was kind of interesting is we looked in the textbooks, the books, to say, what is the ideal gradation? And we found that this curve right here, this bell-shaped curve is the ideal, perfect theoretical gradation. And we made it, and we made a concrete mixture. We sieved it to make it, and it was awful. It was horrible. It was one of the worst concrete mixtures I've ever seen. But one reason why the theory is wrong is that the theory thinks that the mathematical theory tries to use spherical aggregates, and it tries to pack them perfectly together. But in concrete, we don't have that. Our aggregates aren't perfectly spherical. They're a little bit weird shaped, and they're suspended in paste. And so it was very interesting to do this experiment because it didn't work out very well at all. And what happened is our concrete during finishing, when you try to smooth it, before finishing it looked like this. And you know that finishing test I showed you before, the float test, after 8 passes, it looked bad. It took 30 passes to finally make it smooth. And that's not good. That's not a good concrete mixture. So to understand more about this, we actually removed some of these sieves. We removed the 8, the 16, and the 30. And then we gradually added them back in to see what would happen. Basically, the data looked something like this. We had mixtures where we had very low amounts, and the mixture was poor. It wasn't good. And then we had mixtures with very high amounts, and the mixture was poor, and it wasn't good. But then right in the middle, that's where it was good, and that's what we're shooting for. That's what we want inside of our concrete mixtures. So let's talk about these mixtures with the poor finishability at first. If you get too high on this 8 and 16, again, what happens is the concrete, as you start to finish it, it tears. See these lines right here? As you're finishing it, you're tearing the surface of the concrete over and over and over again. And it took 18 passes to finish it. That is poor. That is not good. We don't want that. Now let's talk about the mixture with a poor cohesion. Well, with these mixtures, what happens is in this area, it's mainly coarse aggregate. And in these areas, it's mainly paste. That's not good. We don't want that. That's not what we want. So we have to avoid that. So for cohesion, we need a minimum amount of 20% retained on the 8 through the 30. And for this finishability, for this maximum boundary, we have this 12% on this 8 to 16. So how do I check this coarse sand? How does this work? Well, first question is, are you within the boundary? And then the next question is, you're going to add the amount of 8, 16, and 30 sieves that you have. Yep, the amount of 8, 16, and 30. You total them together and you say, is this number greater than 15%? If it is, that's good. There we did. We total the volume here, and we got 25.6. and we put it up here, and that's what goes in the oval. So the coarse sand is important for finishing and cohesion, and there's limits on the sum of the 8, 16, and 30. They help determine this. Now let's move on to our fine sand. That's the number 30 through the number 200. And we're going to do the same type of thing. We're going to teeter-totter. We're going to start here, and we're going to decrease the amount of sand, and we're going to increase the amount of coarse, of large and intermediate. We're going to move it together. So this is going to go down, and these two are going to go up. This is bad, unusable, and now things are poor, good, 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 moderate, poor, and then unusable. See, this is the same trend I showed you before. When this number is high, it's not good. When these numbers are low, it's not good. When it's in the middle, that's what we want. So this is beneficial here. This is if I have too much sand, oh no, it looks bad. It's hard to finish. If I don't have enough sand, this is what happens. There's not enough paste. It just doesn't work well. And this is right in the middle. This is exactly what we're shooting for. And the slump shows you the same type of thing. If I don't have enough sand, it looks like this. It segregates and falls apart. If I have too much sand, it's stiff, very, very, very stiff. And right in the middle, that's what we're shooting for. And again, we see this segregation. And the amount of sand is really, really important in that. This is where we have mainly paste over here, and this is where we have mainly coarse aggregate. And this is, again, very dangerous, and we don't want this in our concrete mixtures. And another way to show this would be as my fine sand gets too high, my workability is poor, and as my fine sand gets too low, my workability is poor, but right in the middle, that's where things are beneficial. That's what we're shooting for. So how do I check my fine sand? Well, I do the same thing I said before. Is it within the boundary? That's my first check. And then the second check, I'm going to add my number 30, 50, 100, and 200 sieve sizes together. Does this for you. Number 30, 50, 100, and 200 together. And I see I get 28.2%. That's the volume down here. I plot this up in this square, and I see if I'm okay. Now, if I'm doing flowable concrete, like pumpable concrete, like anything over about a 4-inch slump, then I'm going to want 25% to 40% flowable sand. If I want for slip forming, something that's a lot stiffer, then I want 24% to 34% for slip form paving. And that's the Tarantula Curve. That is the value. And why is this so great? It's because if we do this, we don't have to adjust our mixtures. We don't have to change it. We don't have to add water to it. We can just get it the way we want it to be. Now, there's other mixture design procedures that are out there. So I'm going to talk about those. I'm going to talk about the Power 45, and I'm going to talk about the coarseness factor. Now, the Power 45, the concept here is that I plot the sieve number down here, and it's the log of the sieve number versus the percent passing up here. And ideally, you want it to follow this perfect black line right here in the middle. This is the ideal, the mathematically ideal distribution. But what we did is we took all these gradations and we measured their workability, and they were all poor, and we plotted them on the Power 45. And you can see they're all over the place. They're not necessarily close to this black line. Now, the ones that were moderate, the ones that you could use but are still not the best, they look like this. And some of them are closer to the black line, but these are all good. These are amazing concrete mixtures. Unbelievable concrete mixtures. And are they getting closer to the line? I don't think so. I don't think so. I think that there's something missing from this Power 45 chart. And this mix here, this red one, is a poor mix. And it's right in the middle of all the other great ones. And I can't tell the difference. And that's one of the challenges with the Power 45 curve, is that there's some very interesting, useful things going on, but it's about the slope between these 2 points. And it's very hard to tell that by just looking at that. So using a best fit power line on the Power 45 curve just doesn't show us enough detail for the changes in slope of the gradation. It doesn't address the volume of the fine or the coarse sand as well. And the Tarantula Curve is just a very useful tool to make this easier. Now, another chart that's very useful is the coarseness factor chart. Now, this is a plot of the amount of cement and sand you're using, And this is the plot, this curve down here is called the coarseness factor, and it is the ratio of the coarse aggregate to the intermediate aggregate. And a lot of people think that you want to be right here in the middle. You want to be right here in this zone too. But we plotted again. These red ones are the poor ones. These black ones are the very, very good performing ones. And let's look at these two. They're right next to one another. One is poor and one is good, but they have very different performance. And the reason why is that some of these, this Shillstone chart doesn't tell you when you have too much on any one sieve. You can see we exceeded the 20% right here on the 3/4 inch, and the Shillstone chart or the workability chart just doesn't tell you that. So the Power 45, the coarseness factor, all these things were a good start, but they're not complete. And the Tarantula Curve is a simple tool that's being used in many, many states inside the United States, where people are starting to using it to help design their concrete mixtures to make sure that they're right. Now let's talk about using it in the field, because this is great and all, but how do we know it really works? Now this is some data from a state called Minnesota. And what Minnesota says is that they said, we're going to pay you a bonus if you will reduce the amount of cement in your mixture and increase the amount of aggregate. And at first, what people started to do is they did the best they could, and these are where their aggregate gradations fell on the Tarantula Curve. They were all over the place, and the workability was actually not very good at all. And then over time, more and more of their mixtures started to fall inside the Tarantula Curve. And then over time again, more and more mixtures. Eventually in 2010, 98% of their concrete mixtures were within the Tarantula Curve. That's pretty awesome. That's pretty amazing what's going on. Now, why is this so awesome? Well, in 2010, the Tarantula Curve didn't exist. It hadn't been invented yet. These contractors on their own were trying different mixtures, and finding ones that worked and finding other ones that didn't. And they're not going to use the ones that don't work. They're going to want to use the ones that do. So the contractors are finding the same recommendations that we would make for the concrete mixture, but they're doing it on their own without any of the testing that we did. And that's pretty exciting when the field and the laboratory can come together and find the same answers. Another thing that they found is that this is the smoothness of their pavements. And this is the amount of mixtures that were inside the Tarantula. And what happened was, is over time, as more and more mixtures came within the Tarantula Curve, their overall smoothness on their pavements got better and better and better over time. And people want smooth pavements. That's very, very nice. So the Minnesota contractors are producing gradations that fit within the Tarantula and having good success with them. And they're doing this with trial and error and no knowledge of the Tarantula Curve whatsoever. And as more mixtures enter the Tarantula Curve, the smoothness of the pavements got better and better. And I have similar data out for 2 other states that are out there. So how do I get my mixtures into the Tarantula Curve? Well, you usually need at least 3 different aggregate sizes. You need at least a coarse aggregate, an intermediate aggregate, and a fine aggregate. And why? Well, because if one of these are out, you can pull it and you can change it with the other 2. Let me show you what I'm talking about. So here's mixtures where it's percent retained, and here's the sieve analysis. So if this one is too high, then I can pull it down. I can decrease this and increase this. That's why it's helpful to have different size ranges that you can adjust. So do my mixtures have to be within the Tarantula Curve? No, positively not. But if they're not in the Tarantula Curve, you're going to need more paste. Paste, that's binder plus water. That usually means more cost. That usually means less durability. That usually means more challenges for cracking, and we really want durable concrete. So let me show you another example. So in New York City, they called me and they said, Tyler, we'd like you to come and teach us about the Tarantula Curve. And I said, that would be great. I would love to come. And they said, we have a mixture that we would like you to help us with. Now, what they didn't tell me, but this mixture has been looked at very, very closely. They had tried 30 different trial batches of different aggregates, and they said, this is the best one. And they said that they didn't think that it could be made better. They sent me an email and they said, here's this mixture. Could you make it better? So I took it. I took it with my spreadsheet, the same tools I'm going to give you for free, and I just changed some things a little bit, and I sent them a mixture back. Within about 20 minutes, I changed it. This is the mixture that they sent me. Here is the new mixture that I came up with, and I saved them some cement. Let me show you what I'm talking about. This is the mixture that they sent me. And it has too much on the number 4 sieve. It was too much. And so I knew immediately that I could reduce this down. How do you fix this? I could reduce this down and move these up. Reduce the intermediate, move the other ones up. And then I knew that once I did, that I could reduce my binder content. I could make this go down. How did I know that? Well, if they were using 600 pounds of binder previously, and they were happy with their workability, I knew that if I got myself within the Tarantula curve, my workability would get even better, and that therefore I could remove paste, right? Remove paste from the mixture, and it would still have similar workability. So this was a first guess. 550 pounds to 560 is a good guess. With a bridge deck, if I was going to use a pavement, my first guess would be 470 pounds of total binder content. So how did I know where to put these peaks? Well, I don't want to put these peaks right on the line. I want to put them some distance away. That way, if my gradation varies a little bit, then I'm not going to go outside of my limit. So I had them make the concrete with this same gradation. I had them make it, and this is how much the slump was with just water. Then they added some water reducer to it, and the slump got much, much better. This is the same amount of water reducer that they were typically used to using. Then they used just a little bit more, and the slump increased from there. And this helped them better understand how much water reducer they needed versus what their slump was. They were very, very happy with it. It would finish well, it would perform well, and they went out and used it in the field to make bridges and make a lot of other structures around the airport in New York City. It's very exciting for me that my mixture was used there for them. So now how about shrinkage? Now shrinkage is a big deal, especially for cracking, especially for durability. And by removing cement, by removing binder, you can improve your shrinkage of your concrete. And a good estimate is if I'm using 20% SCM and a constant water to cement ratio, then the percentage change in binder is a good estimate of the percentage reduction in shrinkage. Therefore, if I went from 650 pounds per cubic yard to 550 pounds per cubic yard, that's about a 15% reduction in shrinkage. That means that's about a 15% reduction in cracking. And that is great for durability, and that's what we want in our concrete mixtures. It's more sustainable, it's more durable, it's gonna have a lower cost, everyone's gonna be happy, it's gonna be workable as well. So the Tarantula Curve was used to redesign the aggregations and successfully remove binder. And the new mixtures seem to have good workability with a high-range water reducer, and their gradations could be used, could be improved possibly even further if we had a larger aggregate. So now, does the shape of my aggregate matter? Yes, it does. The shape matters, but it matters, but we can actually quantify this. So what we did is we sieved these aggregates to have the exact same gradation inside concrete. So the same size distribution was exactly the same. And one of them needed 0 ounces per hundredweight, no water reducer, to get a 4-inch slump. One of them needed 3 ounces per hundredweight, a little bit of water reducer to get a 4-inch slump. And one of them used a high amount of water reducer to get a 4-inch slump. What's the problem? Notice in this mixture, in this aggregate, it's flat and it's elongated. And these aggregates are kind of in the middle. They're kind of flat, but not very elongated. And these mixtures over here are much more cubical shape. And that's what you want. You want these much more cubical shaped. And so how would you measure this? Well, there's a test, the ASTM D4791 test. And what it does is it measures the long dimension to the short dimension of your aggregate. So it measures, again, the short dimension to the long dimension, the short dimension to the long dimension. This is called the flatness ratio. And the key ratio to compare is 1 to 3. You want 15% of your mixtures, 15% of your aggregates to have less than a 1 to 3 flatness ratio. That's what you want. If you can remove these flat, elongated particles out of your mixture, you're going to get more workability. So do my aggregates have to meet this? Oh, no, they don't. But that means that you'll need more paste to get a satisfactory workability. And remember, more paste means less durability, more cost, and more cracking. So why should you do this? Why should you use the Tarantula Curve? You can reduce your costs. You can improve your strength. You can improve your durability. You can improve your sustainability, and you can get better control over your mixtures over your time. You can get all of these. This is a secret to getting your concrete right. And the reason why is that 75% of the volume of your concrete is made out of aggregates. We have to get that right. So when mixtures are workable, everyone's lives improve. This means they'll be easier to place, easier to drag, consolidate, to finish, to pump. Everyone's going to be happier. This means that the mixtures don't have to be adjusted. You don't have to add water to the site or to the surface of your concrete. It's just going to perform for you and do what you want. So what does this mean? Aggregates are critical to the performance of our concrete mixtures, and simple tools like the Tarantula Curve are very helpful to help us improve our mixtures. And if we get the aggregates just right, then it's easier to control the performance of our concrete. And getting your aggregation right is the first, and I would argue, the most important step to success for your concrete mixtures. And reducing your paste content provides you many, many benefits to your concrete. So that's all I have to say. Thank you so much for watching. You can learn more about me at my website, tylerley.com. You can find and watch my videos at youtube.com/TylerLey. I make videos all about concrete to try to help you learn about concrete. You can follow me on Facebook and Instagram at concrete.tyler, or you can email me at tyler.ley@okstate.edu. Thank you so much. Thank you for watching. Take care, everybody. Bye.